I'm here the scientific director of the BIS Institute. I will say later a little bit more about BIS. There's also changed a little bit, and I'll tell that a little bit at the end. We started here together with the campus, so we're here in the building 2.5 years. We started then together. Rüdolf, Open University and Maastricht University said we want to have a strong knowledge anchorage. And anyhow, this campus is founded by Maastricht University together then with APG and Province of Limburg. And so Maastricht University wants to use these campuses to get into interaction, to get into co-creation, to develop new ways of education, to develop new ways of doing collaborative research with organizations. And my role has been to get that started over the last 3.5 years. But that's not the topic tonight. What I want to talk about, and I was asked to talk about, is artificial intelligence in project management. Now, I'm myself a mathematician, and I have an academic link to project management, funnily enough. So when I started my PhD, I worked on algorithmic methods to predict the duration of projects, and I worked a lot on optimization problems for planning projects under resource constraints. And even my computer science career, so I did mathematics and optimization then, but I also did a lot of system integration. And that was also in that, and there was already a link to AI. So that was in 1990. I was involved in a project where, together with an AI institute, where we said, let us develop a huge set of algorithms, all the algorithms that are available in the academic literature, implement them in one computer system, and it was mostly algorithms on project scheduling, on resource planning and so on predicting, and we want to put all the algorithms together in one system. And the idea was, once you have all the algorithms on project management in the system, you can use the algorithms to improve the system, because any computer system is in a sense also a project management system. So developed that software, and that brought me actually a little bit in AI, in learning and so on, and also in distributed computing. So that's a bit my academic background, so I have linkages, and I have also a slide on that later on, where what I think what is relevant in terms of algorithms and so on in project management, but I'm inviting you to correct me or to add things to that. So that's my background in that area. And then obviously I'm running a big project here since 2.5 or 3.5 years. And we are running a lot of projects within the institute, maybe a much smaller project with a much lower budget than the project that you are responsible for. Okay, so what I will do in the talk is I want to start, now I learned that I don't have to look to the back, I can look here. What I want to do, I want to start with digitization in project management, to give a small, what I think, what could be relevant more in general in terms of what we call now digitization of economy, where are the links to project management. Then I will have a couple of slides where I zoom into some recent developments in AI, those which are mostly in the news, and try to explain to you a little bit about what is actually machine learning, how simple it is, and deep learning a little bit. And then I also want to put that AI, these developments in AI in a broader data science perspective, because a lot what we call AI is actually not really AI. It's not done by AI, it's done by econometricians, statisticians, operations researchers, but it became somehow a synonym for a broader development that we have now other tools available to quantify things, to plan things, and so on. And then at the end I will say a little bit at the innovation method that we're using at BIS and a little bit about the developments. So that's my plan. I want to finish that within an hour, and let's see how that goes. I would really like to have a signal when I'm, say, 15 minutes now at the end, or like that, or 5 minutes. Maybe 15 is safer, then I can start planning do my project management over here and adapt my schedule. Okay, so sorry, this was... now, let me start with digitization and project management. I guess a couple of key problems that I think to remember and that digitization can help. I guess one major problem is definitely to monitor the state of a project. So where are we in the execution of a project? What's really going on? And then maybe updating resource planning, updating predictions. And I guess digitization, and probably you all see that in your daily practice, can have a major impact because we can basically, the information flow is getting better, there are more sensors. If it is a more project where you have to censor information, and team members can exchange better information. So in theory, you should be able to have much better view on the state of a project. And there can be a lot of technology that, or AI and other technology that can help here. The other thing is, certainly, that's what I worked on, is predicting durations of projects, making a planning. So telling your suppliers, your customers, how long will it take your project? And based on what you do the predictions, and then there's a lot of statistics going on. And so the classical PERT method and CPM method, which doesn't work for simple reasons, and to refine these kind of techniques. Then, going a little bit step back, there's obviously the planning of the execution. So how do you actually plan a project? Correct me if I'm wrong, my feeling is that what we did 20 years ago or 30 years ago, when mathematicians as I developed theory, we thought you plan a project up front and then you run it and then we'll see. But I guess nowadays it's much more agile, much more dynamic. You have much more dynamic systems where you basically permanently monitor the state and then adjust your planning and by that get the efficiency, not optimizing an objective up front and knowing then exactly who has what to do. And they are anyhow not available. So I guess I see a confirmation. Adjusting the resource planning. And I think another field that was actually things that I worked on roughly since when I came to Maastricht in 1998, and that is, I guess, really a relevant topic, and I touch it later on a little bit, is what I say here, getting the incentives right. And what I mean is the following. Classically, in optimization, in planning, and so on, scheduling, and so on, we all assumed that there is somehow central data, and then you run a good algorithm, optimization algorithm, and you make this planning, right? Now, in reality, the data is highly distributed, and preferences on the project, on the outcome of the project. So everybody has his own agenda, or her own agenda, so to say. Right? And that is for good reasons, because in many projects there might be parties involved that are different, belong to different business units or to different companies. Now, if you are in such a setting and you ask everybody, tell me about this, and I use it in my planning, you cannot be 100% sure that you got the truth, right? I mean, even if you ask people who are working on your projects, tell me what do you think when the project is ready, they have some strategic incentives to under-report, over-report, to be a little bit optimistic. They're running late and they think, oh well, in the next 2 weeks we catch up, and then it's better not to tell it now because it will be never be seen or whatever. So there's a lot of, in many settings nowadays, there is a lot of asymmetry of information. And that is actually, it's completely not new. Our whole economy works on the basis of asymmetry of information. Otherwise we wouldn't have to have traders who know more than those who buy and those who sell, right, in between. So we have everywhere middlemen, so we have asymmetry of information. But in planning that plays a central role. And I think in that actually in mathematics and computer science, that became very important. That was a side effect of digitization of the internet, that people were looking much more in these incentive programs. So what is, if we use a distributed system, a market platform or any kind of distributed system on the internet, how do we actually get the data correctly to the central computing? How do we get the incentives right? How do we get people reporting their preferences based on what we can make them recommendation, based on what we can make choices? And I think that is something that probably also where a lot of research has been done in recent years, getting incentives right. How do we deal with these different preferences? How do we combine them? And how do we then feed these preferences into decision software, decision support software, and based on that, advise the project manager on how to act and so on. Good. So that seems, and now what am I missing? So where are the key problems in project management where digitization helps already or should help? Is there something missing? Andy? You can have the mic or speak loudly. Oh yes.
The human way of adapting new technology.
I see.
Yeah, just the speed of differs per person to
right.
have something new. You can have like best ideas, but it doesn't mean that everyone can keep up with it.
Right. And to keep really the teams, if you're using a kind of a technology, how can you guarantee that the people adapt it and use it in a proper way and feel comfortable in using it? Yeah, okay, good point, yeah. Others? Yes?
To recognize scope creep. Moving away from the straight line to go. New challenges.
Yeah.
Perhaps request too much detail, moving away.
Yeah. Okay, thank you. Others? Okay, let me then. So I touched it a little bit. I think the opportunities that we have in that field and in many other fields is really that we have advances in the data infrastructure, so we can exchange. We have the whole cloud solution, so we have IoT, we have more sensors. We can basically collect more data. We can use it for collaboration platforms, so we can bring things together from different teams where they can work online on the same system. That is clearly a change over the last years. If I talk about AI, it's very much extending the scope of data that can be analyzed by algorithmic means. So it's not so that the classical numerical data that you have in the ERP system can be analyzed in a better way. It's really the extension of scope. When you saw this small video about this Vera project that we were doing at the BIS Institute, it's really using then sentiment analysis in a call center setting. So that is data that could formerly only analyzed by a human being. Now it can be analyzed by software, by AI software. And then you can feed that into the interaction with the customer in that sense. There are some advantages in predictive and prescriptive analytics. I say more about that, but actually not too many, I would say. And then there's certainly also the whole topic of platform economics, so the digital platforms, the Ubers, the Airbnbs, and so on, that show up also in many other areas, whereby you basically say platform economics is basically we have digital marketplaces and we can organize resources in a more flexible way. Right? It leads to that we can find specialists for a particular problem easily, that we basically get new ways of matching demand and supply on a much more granular basis, also changing a little bit the statics between companies and the different roles that companies have. And the last one is there has been, that has a bit to do with the incentives. There's even a field now that is called social computing. And social computing is about, sometimes it's also called people science. It's really about, can I in a smart way connect human thinking, human brains with systems? So humans interact with the system, and they read something, they act something, they make choices, and then the system takes these choices and then comes to new conclusions. I don't know whether I have a slide later, so maybe if I have it, I skip it then. But I give you an example that is been developed in that context, and it has again to do with project management. Now, what people tried out is the following. It's very difficult to predict really the duration of a project often. If many people are involved, and it has to do with because people have their own gut feeling or they have information that they cannot reveal, that they don't want to reveal. Now, you could all ask them, send them emails, and then send them questionnaires. That would be one way, and then analyzing the answers of the questionnaires, you could try to make a new prediction. But what you also can do is you can set up a prediction market. And that market works as follows. You are trading kind of futures, financial items, and say, okay, I have a financial item that pays off for every day, let's say between 1 month and 2 months from now, for these 31 days. For every day I have a financial, I have a digital virtual good, right? And I say, if the project ends on that day, everybody who owns these shares for that day is paid per share, let's say 10 euro.
That's called blackmail.
Sorry, blackmail?
That's called blackmail.
I don't see the connection. Probably the product is called blackmail, or what do you mean?
Well, when you are asking people to do something, and you've got the idea that without some kind of an incentive, like a share or part of a share, they're not going to do it, I call it blackmail.
Yeah, but here it works differently. I don't give incentives for the people to work harder, so I try to get a prediction. So I tell these people, so I pay out the shares and then I didn't tell the second part. So I have these shares and they pay out if that is the realization of the day. Now, and then I put shares for every day in the market and I let people trade these shares. Right? So I give them an endowment of shares and they can buy and sell these shares. There is an issue related to that blackmail, but wait a second. So I trade these shares. It's called a prediction market. And then the price of the share, as in every market, the price of a share of a company basically represents the fundamental value, what people think the company, the value of the company is. Not perfectly? Okay. Now, then you will see different prices for different days, right? And that gives you a kind of a distribution of prices, and that turns out to be often a very good prediction for the right duration of the project, because there will be everybody in the project. The only thing where you have to be really careful is that you don't have traders that you don't have participants in the project who are at such a critical point that they can determine when the project ends, that they can delay the project. So that is a little bit the backside of the method. So it's a little bit difficult to get that right. But in principle, using basically shares on an event that's going to happen in future and trying to translate the value of the information into a value of that share and paying it out works pretty well for prediction markets, for predicting the sales of a new product. So companies tried that out. They were trading basically sales figures for the first week or movie sales figures for the first week of showing a big movie. You trade these things, you give people partial information, and they trade on the market, and that gives you very good predictions. And that is social computing. And one second, this is social computing in the sense that you use this human brains of giving partial information, talking to each other. You translate it into a buy or sell, and on the platform you have the market platform where basically a double auction is taking place. You had a question?
Yeah, aren't you afraid that you can get into a situation like Ticketmaster descriptions give, and for a few years already, required to buy all tickets, and then with that determining?
Yeah, I mean, I said already, it's a nice idea. If you implement it in practice, you have to be really careful that the market cannot be widely manipulated, right? Sure. So you have to see, I mean, that's been, on the stock market you also have to be careful who is allowed to trade.
No, but you
and then the project management problem is usually both those who are responsible for the execution are the same people who are trading in the market. So you would have to take a particular group of people, so like, let's say the secretaries or the project managers, and say maybe or something like that. Yeah?
But Ryanair applied it very well, because they are doing exactly the same with their ticket prices.
That they
when you follow
yeah?
the price of a ticket.
Take the mic, please.
When you follow the price of a ticket, let's say from half a year in front up till half an hour before takeoff,
yeah,
then you see a certain optimum as well. They applied this, let's say, this kind of algorithms that you're telling us.
I'm not sure. I would doubt. I would say what they do is they do dynamic revenue management. So basically, based on the sales so far, based on the available seats that they still have, they dynamically adjust the prices to get their flights full. Okay, but let's not go to the break. For the break. Okay, otherwise I don't even get to slides. So, okay, so that is a little bit, just a few examples, and I go into the next slide, I go into AI. This is a little bit a slide that I get back to later again. And to put all, I like to give that also more or less in the beginning of my talks. There are two things of it. One is that there is AI or data science there are different kind of data analytics or data science methods that you can use, and it's good to distinguish them. So there is a descriptive diagnostic that all has to do to understanding the state of the world and why the state of the world is like it is. But then you're looking to now and in the past, and then you have the predictive analytics. It's basically making predictions, what's going to happen in future, and prescriptive is really giving recommendations on how to act for the future. So in predictive, you don't change, you simply you basically predict the events that are going to happen due to whatever, and prescriptive, you take actions. And then in prescriptive analytics, you can still have decision support, or you have decision automation. And a self-driving car would be on the lower one. It would be really prescriptive analytics, what to do, that the car has to know what to do, and it takes its action itself. Now the other important thing is, so that is a little bit good later when I talk about different AI approaches. The other important thing is that there is always a human input, like you said already. So there is always an interface to the human, and especially if you use prescriptive diagnostic algorithmics, and it's always very important to understand that interface. So whatever algorithm, whatever tool you build, it only works if you have a good idea of how it's going to be used. And that's also why we have the second lecture by Kai, who focuses then really on the even just the visualization part of it. How do people look at information, at graphs, at pictures, at gun charts, and how can you make a difference by presenting things in a different way? Good. Now, recent progress in AI. I have to. Yeah, maybe I should change the arm at some point. Recent project in AI, and I think it's fair to say that what you mostly read about when you read about artificial intelligence is some form of machine learning. So if you read the news, people are saying artificial intelligence is about software that learns to improve itself, right? As if artificial intelligence is about you write a program, a computer program in some language, and then this program is changing over time. Its statement, for loop is a little bit changed, and an if statement is a little bit changed. I don't know whether you are familiar with programming. It's not as much as that, but there is a lot of the learning in artificial intelligence is basically what makes the hype. That there is somehow from using the algorithms, training them in the beginning, using them, they get better and better and better, and that is the idea. And then there are some people who say that it's growing exponentially, and so we are getting into, and they learn to program themselves, and then if something is growing, well, why should there be an end? And then the computers are taking over and so on. I'm not one of these people who believe that. So I think we should be quite modest in what we can expect from machine learning. It has its advantages, and I'm not alone in that sense. So basically, it's based also what I read from leading AI researchers. So recently, I read an article in Communications of the ACM, American Computing Machinery Association. And Professor from University of California, who really stated, he said, there's no progress in AI over the last 10 years. There's only progress in applying AI. And that gave it a lot of boost, there's commercial value in it, but our principal problems were not much smarter than 10 years ago. There are a few deep learning and few ideas, but we can be modest. Anyhow, but you can do things with machine learning. And it requires a lot of training data, it requires a lot of computation sources, especially the training data puts often harsh limits. So if you are working with too few cases, you can't do anything. It is not enough to learn for a computer program. In the core, actually, machine learning is optimization. Funnily, it's really solving a mathematical optimization problem, and I try to tell you in a second how that looks like, maybe along that picture. So this is machine learning 1989. And it was already not too bad then. So this describes a system that was really used in practice by the US Postal System in 1989. And what does it? It basically, it's now not needed anymore because we don't write letters anymore. But at that time, people were writing letters and handwritten letters and would put postal codes on the letter, and it would be perfect if a machine can read the postal code, recognize the numbers, and translate them in a proper digital representation. Okay, and that worked. And you see also a little bit how such a neural network, or that's basically a neural network. So basically, it's just 2 layers here, or 3 layers, or 1 middle layer. And what you have to imagine is that this is nothing more than learning a mathematical function. Why a mathematical function? Well, the mathematical function underlying this problem is very, very simple. I can explain it to my kids, right? Because the input is, if you look at such a number, or look at such a number, the 2 here, it's just a lot of black and white pixels, right? Take a digital photo, and then you have pixels, black or white, and maybe gray or in between. It's just, let's say, you have a resolution of 5 megapixels, you have just 5 million pixels, right? And this is wonderful input for a computer. It's 0 or 1, let's say, if you forget about gray. And the output is one of the numbers from 0 to 9. That's all. And what we do, if you look here, you have a computer you have a mathematical function implemented in your brain, starting with your eyes. You get the pixels, and if I ask you to read a number, you have a voice generation machine that says the right number. And as mathematicians, I say it's just a function, right? It's a function that maps the pixels into a number, into a sound signal that represents a number. Now, in that function now the funny thing is that we have no clue how our brain does that, and how we have a lot of research how the eyes read and how we speak and what's going on in here and so on, but we don't really have a mathematical representation of that function, right? There's no neuropsychologist or whatever who could write down that function. But what works is that you can train a kind of a relatively simple mathematical network to learn that function. And what you basically do is you say, and let's go from bottom to top, you put here into these many data points, you put all these pixels. And then all these pixels, any of these pixels is somehow connected to, let's say, a data point here. So just a little bit memory in the computer. And on all of these arcs, there is a mathematical transformation. You take what is here and transform it mathematically, exponential functions, quadratic functions, or whatever. You transform it into another number. And then in these points, the transformation of many is collected into one big formula, and that produces another number. And this number is again sent to all this, to the 0 to the 9. And there again, there is a kind of a black box mathematical formula that transforms that into yes or no, whether it's a 0 and so on. Right? And I don't have the function at hand, but you could write down these functions, and in these functions, in these mathematical expressions, you will see many parameters. That's basically things that can be adjusted, like in your parameters, I guess that's clear, right? You can change them a little bit. And in the beginning, you start just with any setting of these parameters. And then you feed, and then you execute this mathematical function, and you see, look, what is the result? And then in the beginning, it will be always wrong, almost always. But by any of these mistakes, you simply change a little bit the parameters, right? And that is the learning. So that is feedback learning. So basically, on all these billions of mistakes that the system makes, you always change it a little bit. And at the end of the day, you have learned good parameters. And if you build this network complicated enough, it's surprisingly that you get basically 100% perfect approximations. Right? It will never be always correct, but it will be correct in almost all cases. And basically, and then you can go out and you can write down these mathematical functions, and you can ask a neuroscientist, can you make sense of it? No, for sure not. He just sees millions of parameters. That doesn't make sense. But basically, the system can learn that, right? And it's basically a statistical approximation. It's a model that is by itself doesn't explain anything, but the model approximates good this mathematical function that we have in our brain when we start or develop in our brain when we learn to read numbers when you are 3 or 4, I don't know which age. Right? So that's it. Right? And why is it optimization? Right? As a mathematicians, I say every possible function there lives in this 1 million dimensional space. And so there's all the parameters in one list that gives you a dimension of 10 million, say. And in this space, I'm searching the right point that represents the right function. And then I start somewhere, and I try to optimize and move in the search in this space to get to the right point. That's it. And that's machine learning in 1989. And then you get now in recent years, we got much better in that, so that's 2017. And in some sense, this is again the same thing. So that is basically you give a picture, and the machine learning has to identify where are the faces, and then identify emotions on the faces, and then replace the emotions by the right emoji. And then the network looks like that, right? And again, it's a mathematical function. It's just a little bit more complicated. And then a big breakthrough was why it's called deep learning, is that you say that they found out that if you connect all these, there are certain features, so you have certain kind of layers in here that are good that can be trained for particular features, distinguishing colors, distinguishing shapes, and whatever. So that is kind of, so the engineers who build this deep learning, they have learned which feature extraction is important for a particular task, and in which order do I build that in my Lego system, and how do I train them, and how do I organize the feedback, and there's this feedback and that feedback. I don't know, and there compare very classical steepest descent methods that we learned in school from Newton, they still work. There are some very old methods that turn out to work that converge very fast. And very often it doesn't work. Sure. But it just, and that's what you can do nowadays with deep learning. Yes? And that is what I called in the previous slide, that is supervised learning. So these are examples from supervised learning where you basically have to give the system enough correct answers, and based on that it can do the classification. There's also unsupervised learning. They use it usually in clustering, where you say I give millions of data points that represent somehow observed consumer behavior, and I try to understand, are there certain patterns? Can I group my consumers in 4 typical groups? And I give the computer the task, cluster them in 4 typical groups. I don't have any semantics of that group, but I will simply use as a mathematical structure. I identify clusters, and then I look at the clusters. Oh yeah, that makes sense, or doesn't make sense, right? So in that sense, that would be. You have also examples of unsupervised learning. And in a sense, it's also social computing, because you need the human brain as an important input. It's not that the machine learns it itself. And you have a system by Amazon Turk, where you can hire people to help you. Right? People are paid for saying it's a cat or it's a dog, or for training annotating the data. Right? And it works not perfect. So there are a lot of examples discussed in the literature where you take such a picture and you change 5 pixels, something that a human eye can never see, and it goes wrong after that. So if you trigger the system at the right data point, you make the mathematical system unstable. Now, but I think the main message that I want to give you with these examples is really that at the bottom line is that we can now train a certain class of mathematical functions, and if we have enough data, and if the problem allows it, you can do fantastic tasks that you think were unbelievable. But it only works if there is such a mathematical function underlying the problem. If it doesn't exist, I don't know, for whatever reason, you cannot solve a huge project planning problem by that. You cannot give you your project planning problem and say make the optimal schedule. You never have enough data and so on for that. So there are many, many tasks that you cannot do. Even making predictive models is quite hard. So, but it has many good applications, right? And that is another typical application that many people use in their presentations, where you give 2 pictures. One painting, Van Gogh, and you do a picture, and then basically it's again a mathematical function. Why not? Right? So it's basically creating a new set of many, many pixels that have an optimal distance to Van Gogh and to the picture of the dog that I took. Right? So I mean there are two huge pixel vectors, the dog and the Van Gogh painting. And give me something in the middle, or give me something that is somehow in some way in aesthetic dimensions has enough Van Gogh, and in terms of reality has enough of the dog, right? And then you can write down whatever that means in mathematical formulas, and then you can need enough data, and then you can learn that. It's fascinating, but it is also not that I say that these AI people are not brilliant researchers, but it is not so wow. It has also its limits. Now let me give you another example that recently made the news, and it all started with implementing by IBM Watson the first, even earlier the first chess programs, and then IBM Watson had this success in Jacuzzi, and then people started to look at Go, for example, and recently also poker. And so Go is a tremendously complicated game. The rules are relatively simple, but playing it on a master level is extremely, extremely difficult. at the end of the day, it's really putting white and black dots on a field of, I don't know, 32 by 32 or something like that, right? But it has, what makes it complicated? Now, if you, in game theory, we would say mathematically, we would represent such a game by something that we call a game tree. Now, a game tree is a tree upside down, so it has the leaves down and then the root up there, and it goes basically. And in the very first node of this game tree, in the root of the game tree, there are all the moves that the first player can make. Right? And it's 32 by 32. It's going to choose. I think that it's less. Anyhow, it's 24. Let's say 24 by 24, 20 by 20 moves. 400 moves. Now, after this player has made a move, the next player has one move less, right? And maybe something is not feasible. This thing explodes, right? And if you write down all the points of this game tree, you need as many points as the following number. Take all atoms in the universe, replace every atom by another universe, and count the atoms in this new universe. These are the nodes of the game tree. Okay. Now, playing Go is nothing else than finding your way in this tree, right? And with a lot of experience, you can exclude a lot of things. But now, machine learning and huge computing power can do that more efficiently. But it's solving a nasty, big problem, and so certain parts of the game tree you better don't go into. And that is basically, not every move is a good first move or a second good and so on. It's the same in chess, right? In Go, it's just much more, right? Now, but amazingly, we are now at a stage where with machine learning and so on, and reinforcement learning, what you now do actually is, because you cannot annotate good moves anymore, you let the computers play against each other. Right? And many times. Right? And every time they lose, they learn a little bit. And then you give them a feedback, and so on, you analyze what happened and so on. And here is how fast a computer can learn. I don't know if I've seen that before. So this is basically AlphaGo's success rate, so by Google AlphaGo. So this is the level in whatever ELO rating, whatever that means, of the best Go player in the world right now. This is time in hours. And this is the ELO level of a Go program, of AlphaGo, the learning curve of that program. And you see here with reinforcement learning, after roughly 35 hours of playing, the program is better than the best player in the world. And this program has only the knowledge of the game, the rules. There is no libraries, no books, nothing, there's no training, no human training. It's a stupid computer program that starts with the rules and that learns in 35 hours to be better than the best Go player in the world. And then you can do that with other kinds of supervised learning. Yeah, then it's like that. Right? So that is, in a sense, it's fascinating. But again, I then say, well, mathematically, well, this is the game tree of Go is huge, but it is pretty much structured. Now, there's also poker. Poker is a bit more complicated because now you think in poker you can cheat a little bit and you can bluff a little bit and so on. And still, in poker is also now computer programs can defeat the best poker players. And it's not that they learn to, with emotion recognition, look into the face of their human counterpart and learn how to play. It's simply they can analyze the game tree damn good and damn fast, right? And they're learning even they play them many rounds, and they learn a little bit how the opposite opponent is playing. So it's not it's an opponent-dependent strategy that they learn, but they are simply extremely good in processing that information. Good. Now, if you look at that a little bit critical, on one side, I think there are fascinating applications for that, and they are mostly, if you go back to the analytics graph, they are mostly in the prescriptive and descriptive, and a little bit, in the descriptive analytics and diagnostic analytics. If you go to predictive, it's difficult. Playing Go is in a sense prescriptive because you have to make moves actively. So in a sense it is a very narrow but an amazing progress in prescriptive analytics. But if you go to the real games that you are playing in your project schemes, in your daily, I'm playing daily in all kinds of dimensions, project leading people and so on, even in research, it's a completely different game. And expecting that a computer program that can essentially truncate a search tree efficiently or learn a mathematical function, expecting that that can replace our work is far-fetched. Because it would basically say all what we do is permanently applying a mathematical function. That would be very functional. Right? This is my input, now I do this. Now I do that. And no, it's not how we live, it's not how we interact. Good. So that's one point. So I think when there's a lot still more to be done, but it can easily be that after another 2 years we say, oh, now we harvested all the low-hanging fruit with deep learning, and now we're getting to the real challenges. We want to have statistical certainty. We want to have reliability. If you take the self-driving car, it's also a reactive system dynamically, but at which point do we get the qualities that we need in these systems? And the other critical thing is, and that is, one can debate a lot about that, to which extent we don't get really new insights, right? Often. If the simple postal code, a neuroscientist will not learn something from the fact that a machine learning program can read handwritten postal codes. Because these numbers in the model don't tell enough. And if we and there is certainly a debate, and if you now move more and more to these black box machine learning models, it's not only that people might not accept them because you can't explain them to people, even the scientists don't understand them, but it's also that maybe we don't make progress in the underlying scientific areas because at the end we want to understand how our brain works, or at the end we want to understand how markets work. At the end, we want to understand in finance what really determines changes in the value of a company. What are good strategies and so on. We don't want to have a black box that tells the management of a company, do this, based on machine learning of 1,000 other similar companies in the world. Right? We want to get this deep understanding. Do we get it? Interesting. Okay. So there are advantages and there are also these disadvantages that I just mentioned. And there are also a lot of flaws in seeing causalities and correlations where there are more none, and many people, I don't have one example in my head at that time of the day. But the basic thing is it's going to be an enormous helpful tool, especially for cognitive things. But if you go deeper understanding, getting statistical sound information is much more difficult. Good. So we are back to that slide. How much time do I have left? 20. So that's good. So we are back to that slide, and then let me dive a little bit deeper into the descriptive and into these 4 areas, and somehow summarize a little bit again and see what I didn't say here. And then at the end I do a little bit on the BIS and example. So what I think is that if you look at purely cognitive tasks, so like clustering, pattern recognition, natural language processing, translating text from different languages, there's a lot still to come in AI, right? If you now simply look at the quality of translation programs, I'm not paid by Google, but let me just mention Google again. If you look at Google Translate, it's just, I find it, I use it now, I really started using it when I'm not sure whether I'm writing a proper Dutch sentence and I have the feeling it should be proper. I'm typing it in Google Translate, I let it translate to German, and then I see, oh, this is not a good German sentence. And then I correct the German sentence, I translate it back into Dutch, and I get a better Dutch sentence. It works. Well, I still need, I probably didn't have the feedback loop closed, because who tells me that, how can I know that it is a better Dutch sentence? Well, that is the other story of it. But I got the feeling that, oh yeah, this sounds much more correct. So I find mistakes that I constantly make. And my son learns French now, and in English in the secondary school. I mean, they're cheating all the time, right? I mean, it's simply on Google. If you have to make a translation, right? I don't know how he does it at school, but I don't know how he does it, how he gets fixed. But they learn it. You see, it's also you learn from that. And these are simple things that basically have sufficient structure, and there's no reason at all why not let a computer do these simple things that have sufficient structure. Where these mathematical functions work, let them do it. We are not doing our bookkeeping in handwritten books since a couple of years, right? Don't we? Right? We have ERP systems, we have databases, we have computers, and so on. Let's do that. So the other thing is any form of digitized data can be analyzed, at least on a descriptive level. That is really recognizing emotions. It's really impressive what you can do in recognizing emotions once you have trained a data set. Translating in a business value is maybe another story, but it's amazing what you can do there. And even if you can flaw this thing by changing some pixels, it's still very helpful in many applications. Probably people are working on reducing the size of the data set that is needed for training purposes. By that you widen the scope of applications, right? If you can learn things from less data, you can basically use it also in applications where you don't have so much data. The conversion rates are getting better, the hardware is getting better, right? We were going to hear about blockchain and the special hardware that it has been developed for blockchain probably, and the same is for machine learning. You know what really, also from the hardware perspective, what helped so much that we have so good machine learning, deep learning algorithms nowadays? What helped? All in the audience helped who were playing computer games between 2000 and 2010. I mean, these vector machines, the hardware that was necessary to make computer games working on your PC is now the hardware that makes machine learning affordable. So you don't need supercomputers. All the parallelism in the hardware that you needed there to make these moving images, and the sound, so mostly the moving images, is exactly what you can use in these layers of the machine learning network. That made a big improvement there. And I think the question here is, so technically I think we will see more progress, and I think the interesting discussion is really at this point where the blue and the red part in the diagram basically meet, right? So basically the human interface. So to which extent, how can we combine these cognitive support systems, as I might call them, with the human being? Is it acceptable? Will people like it? Will people learn to work with it? I'm optimistic, but it will require particular engineering, right? We also needed a couple of years to design cars in which we, as long as we drive properly, drive very safely. Right? 20, 30, 40 years ago, you didn't have to make a mistake to get into a severe car accident. Now, others might make a mistake, but it's still, so we improve this design and we learn what works with our human cognition in combination. Okay, if you look at predictive analytics, it's getting much more difficult. One thing is, that I always like to mention is that if you go into predictive analytics, it's even more important to understand the interface with the human being. And Kai is already preparing them, his last slides up there. He will tell more about that. And that has all to do with, I think that has all to do with the way how we can, whether we as human beings understand statistics. There are two very nice books on that. One is by Kahneman. He's a psychologist who won a Nobel Prize in Economics in 2005 or 6. And he has written a wonderful book that Thinking Fast and Thinking Fast and Slow. And in his book he explains very nicely that we are very, very bad in understanding numbers, interpreting statistics, interpreting probabilities, and so on. We make really permanent mistakes. And if you give people better tools and give them statistics, it doesn't mean that they can act on that. And where does it come from? And there is a lot of neuroscience research that has been done on that over the last years, since his research, basically. So the thinking fast and thinking slow stands for two areas in our brain. So we have a thinking fast area and we have a thinking slow area. And the problem is that most of our actions are based on thinking fast. And that is just by evolution, right? If you are in the wilderness and the lion is coming, you better think fast than act slow, right? You have to use a heuristic. And we use, I think a colleague here from BIS told me that there's a whole category. We have 40 different psychological heuristics that we're permanently using. And these are heuristics, also like in mathematics, they are approximate solutions, and they can be pretty bad. Right? Most of the time they are good. But we are using all the time these heuristics. We are using this thinking fast machine, is always working. Now there is also a reason, and the thinking slow machine is not only slow, it's also lazy. The thinking slow machine is really happy with the thinking fast machine is going to recommend. Right? And that has also very clear reasons. Because the amount of food that we can eat with our little stomach in the morning would not give enough energy to do thinking fast all the day, or we would be permanently in the cafeteria. Right? Coffee helps a little bit, but not really. Right? So it's also economically that our thinking fast machine has to work a lot, and thinking slow is basically only activated when it is really needed, or we have really time and the patience and so on. But this mechanism works when we are working in a digital environment in the same way as our predecessors are running in the wilderness, right? We will interpret all this digital information on our screens with our thinking slow machine, and not with our thinking fast machine. We will have heuristics in interpreting it. And I think in our design, we have to be very careful to take that into account and do research on that. How does it really work? That's part of what we're doing at this. The other one that's a little bit related to that and explains a little bit is a wonderful book. It's very critical by Cathy O'Neill, and that's called Weapons of Math Destruction. So look at the DH. It's not math destruction, it's weapons of math destruction. It gives you a lot of examples how if you use data science, statistics, predictive analytics, AI, clustering, how people simply start believing it without questioning the recommendations. And they start believing it because they're in this thinking, firstly they're in this thinking fast mode, or they were relatively, they have never learned to interpret these things properly. And they were never told that things have to be analyzed a little bit more carefully. And I think getting back to this a little bit fundamental criticism of AI that I like to share a little bit. See, the more we go into black box machine learning approaches, and if we are going to educate our business students and our economic students just by machine learning approaches, it's a little bit like what happened when we gave these kids the pocket calculator and that didn't teach them to calculate by brain, right? So, and to do it by hand. So there's a danger also in that. And that danger fits with our natural thinking fast and thinking slow biology, right? So, also that. And then simply, but if you go back to computer science, you will also see that making statistically sound predictions with a machine learning model is also very tough. You can't do that. You need the mathematical insight, the statistical knowledge. You have to put them into your model, and then you can calibrate a model, you can optimize a model. And if you throw that all away, you lose too much of knowledge that has been developed over 15 years. What you can do is you can combine the two. You can build hybrid methods where you basically say, I do time series analysis, I have 100 variables in my time series models, and no statistical econometric model can handle that, but I can use a computer to select the relevant variables by machine learning. So I do a classical approach, make a prediction with 5 variables, and then I throw away one of them and replace it by the other. And that machine learning can be done then again with machine learning. So there are hybrid methods that will probably help us to build better tools. And if you really go into prescriptive analytics, I think there will be still some time where we are going to show students that one, and that is already, I guess, a math student, that's one engineering student, a business student would run away already, he wouldn't understand the sigmas. But so these kind of models will still for some time play a role here. And again, you see developments in hybrid methods for optimization problems where you simply have many different approaches to solve such a problem, and the machine learning is helped to select some parameters on parameterizing the computation and so on. So you see that we can use this learning in some context, but it will not be that a black box can simply solve such a mathematical optimization problem. The same, I think I skipped that given the time. I think there's another one that's a nice example that was done by, I forgot your first name, Frank Teusmann and Olga, I think Olga Stankova from Maastricht University. And it shows a little bit how other fields that have been developed in the quantitative field of economics or mathematics over the last years can nowadays, in this digital kind of context, can start to play a role. And thank you. And in this case, it's related to strategic decision making, and what they basically combined is cancer therapy with game theory. How can you combine that? Now there's a theory on evolutionary game theory. So basically you have basically a stylized model system of small players, and you put them in a game of strategic interaction, and you play them against each other, and they have different strategies, and then you see how does this system, what strategies are evolving over time, what strategies are fit, have a high fitness, and then what strategies survive many millions of generations, right? And there has been theory developed over when such a system stabilizes, certain trends in the system. That field is called evolutionary game theory. And now it turns out that you can use that theory in cancer treatment. And in cancer treatment, you have the cancer. These are all small cells that are in your body, or the body of a patient who has cancer. There are many small cells. And all these cells have their own survival strategy. They want to grow, they want to become bigger, and I don't know whether the cells know what they are doing with the human body in which they are sitting, but they have their own preferences. Right? Now typically what the doctor, and the doctor is basically the opponent, right? He's playing a game, in a sense. A game is a strange word, but mathematically I say it's a game against these cancer cells. And the treatment is basically pushing these cells in a particular direction. Now, what you typically would do is you give the maximum doses of whatever, of radiotherapy, just to make it still somehow survivable or comfortable or whatever, however you define it for the patient. But if you treat these cancer cells with the maximum doses, you might actually accelerate evolution among them, and you might basically get the opposite effect. and treating them in a more modest way, turns out that you get better convergence of the evolutionary system. And that is known in game theory. So in evolutionary game theory, we have learned how to modestly trigger a system to get into a particular state. And there's now this group here at Maastricht University, they're working international team, but also some other groups who are really working on using evolutionary game theory in this kind of cancer treatments. And that is, now probably they want to, that is also happening these days next to AI. Now at some, probably they will say this is also artificial intelligence, because if they say this is artificial intelligence, they get extra funding. But strictly speaking, it's not artificial intelligence. But just to give you an idea, that this development of multitude infrastructure, better computing power, all the mathematical theory that we have developed over the last 40, 50 years is now getting more and more impact. I'm now out of time, right? Good, 2 minutes. Let me finally say a little bit, a few words, 2 minutes, what we are doing here. We started here as a Business Intelligence and Smart Services Institute. We have with Hochschule, with Open University and Maastricht University. I'm from Maastricht University. Now we are, after 3.5 years, we think we can bring in much more our own strengths by having 3 expertise centers here. So from now on, we will have Rüdolf will have its own expertise center. This guy, for example, in data visualization. We will have an expertise center by Open University. We will have a follow-up of BIS, of the old BIS. We give it a little bit different name. We call it now the Brightlands Institute for Digital Smart Societies. The D doesn't have a place in the acronym, but we didn't want to change the acronym for the moment. And what you see here is a little bit, I guess, what I tried also to transfer in my presentation. I think that the key thing that we have to work on nowadays is take all this digital technology, this algorithmic technology, this data, and analyze the interface as the green part of the picture. Take the blue area, and wherever we are in technology, are we on the descriptive, prescriptive, and so on, analyze the blue part, the interface with the blue part. And we are going to do that in legal analysis, we are going to do that in neuroscience, cognitive networks, we are going to do definitely in health, we are looking at smart digital society. So basically, I think it's time to improve and to work on a better understanding how we can embed the fantastic opportunities of these technologies in a meaningful way, a sustainable way, into the real problems that we have as mankind. And don't forget, and on that level, don't forget the human. And here's my last quote, and I think also related to the point that I want to make. Machine learning is not, AI is not taking over, and there's a nice quote by Konrad Zuse. Who knows who Konrad Zuse is? The Germans among us might know. Yeah, he developed, you can see, he developed parallel to von Neumann, the first computer in the world, and Berlin is still in the museum. And Konrad Zuse said so nicely, die Gefahr, dass der Computer wird wie der Mensch, ist nicht so groß, wie die Gefahr, dass der Mensch wird wie der Computer. So, that's my last sentence here, and we probably don't have time for that slide, but we can do it in the break. But maybe two questions are allowed. Thank you very much.
No questions?
Good.
What I find interesting is to see that a lot is being set up based on what can the computer do. I would like to turn it around and say, where can the computer help? What does the human need? In 1995, in my former work, we set up a very simple decision support system. Not with all kinds of intelligent computers behind it, but just working that other way around. We had a lot of managers in post offices that needed to staff their offices, and we just checked what do they miss, and where are they good at. And the interesting thing is that by just giving them the average number of staff that they needed based on the data of the last year, they had to estimate and think of all the fluctuations, if there were days off, if there were busy periods and stuff like that. They did that well that they had 30% more productivity where it was implemented than in the parts of the country where it wasn't implemented. I think that also each type of developments should think the other way around. Where does human need help? And what can the computer do?
I fully agree. And that is also why we have start questioning. That is basically, we first start with the questions of the needs of users, and we're not coming with selling them the technology or trying to apply the technology. And in the dialogue, you will find out where is really help needed and what can be added. It's also a nice example what you say, by just giving them the right single number to these people, that you have a big impact. There are also examples in this Kahneman book where they simply gave them something complicated and it had no effect at all. But by giving just one number, that was the key. And I think understanding what are these keys is really important. And then you get easy, scalable, simple solutions, no IT nightmares and so on, and effect. Very good point.